Hello guys, welcome to Physics Grad. This is day 2 of daily quantum mechanics, and in this video we are going to see what are the implications of the definition that we have seen of linear vector spaces. Okay, so what do the definition and the features that we have seen in day 1, what do they imply? They imply some important results, and that is what we are going to see in this video. Okay, so in this video we are going to see and prove as well some important results that are implied by the definition and features of linear vector space. And once we have done that, we are going to consider one example and check if that particular case is indeed a linear vector space or not. So let us begin. So this is the definition that we had discussed in the previous video in detail. So this is just for you to recall. So I'm just going to skim through this very fast, and if you want to review this, you can just pause the video and see. So this was the definition, and these are the features of a linear vector space. They must be closed under addition and scalar multiplication. They must have the distributive property. They must be having the this got erased, associative property. But yeah, you have seen this already. They must be commutative with respect to addition. There must exist a null vector, and there must exist inverse vector under addition. So all of these things we have already seen. Now these properties of linear vector spaces are going to imply some very important results which may look obvious to you when you look at it for the first time, but they are very important in constructing a particular structure which we can use to represent quantum systems and thereby write equations which describe them and therefore help us to verify results of experiments and so on. So these results are the main points which help us in constructing further structures using which we can represent quantum systems. So that is why they are very important, although they will look very obvious to you when you look at it for the first time. So these are the results which are implied by the axioms that we have discussed so far. So the first one is that the null vector is going to be unique. So that means that if there is some other vector which has the properties of a null vector, then that has to be the same as the null vector. There cannot be two null vectors for a given vector space. Also, if you multiply any vector with the number 0, the result of that multiplication is going to be a null vector. And the inverse vector under addition of a vector v is going to be nothing but equal to -1 times the original vector v. And the inverse vector under addition is also unique. Okay, so in the next few minutes we are going to prove these results using some elementary logical reasoning. So let us do that. So first we are going to prove that the null vector is indeed unique. So for that, let us assume that there are two null vectors which I call 0, 1 and 0, 2, and I am assuming that they are two different null vectors. Then this would imply that adding 0, 1 and 0, 2 will give 0, 1. This is assuming that both of them are null vectors. So here if we assume that 0, 2 is a null vector, then using this property, if we call this as 0, 2 plus v as 0, 1, then this result is actually 0, 1, and that is what I have written here. Similarly, if we have 0, 1 plus 0, 2 in such a way that we consider 0, 1 as the null vector, then the result of this must be same as this vector, which is 0, 2. But these two quantities are the same, and therefore these two must be equal, which means that 0, 1 must be equal to 0, 2. But we had initially assumed that they are two different null vectors. So equality here will imply that our assumption is wrong, and therefore our null vector is going to be unique. Alright. So next we go on to prove that 0 multiplied with any vector is going to result in a null vector. So first we write this guy as 0 times v plus a null vector, because anything adding any vector when added with a null vector is going to give back the same vector, that is this property. Now this null vector can be expanded as v plus the additive inverse of v. That's because the sum of those two quantities is going to be a null vector. And now I am going to use this property, which is the distributive property under the scalars, and combine these two guys and call them and write them as 0 plus 1 times vector v plus the additive inverse of vector v. Now this is going to become just v plus minus plus inverse of v, which is nothing but the null vector. So 0 multiplied with the vector is going to give a null vector. Okay. Next, the additive inverse of a vector v is nothing but it is equal to minus 1 multiplied with the original vector v. So for this we consider v plus minus 1 times v. This should be equal to v plus minus v, and if we combine them using the distributive property as we did earlier for one of the other proofs, this is going to be 1 plus minus v times v, but 1 plus minus 1 is nothing but 0, and we already proved that 0 multiplied with any vector v is going to give us the null vector. Also v plus minus v, or sorry, v plus the additive inverse of v should also give the null vector, which is one of the properties that we have seen. So this implies that these two quantities must be same as this. Okay, so this quantity must be same as this because both are resulting in the null vector. So therefore this is equal to this, and from the properties of addition, if you have two different things being added to the same thing, okay, and it is giving the same result in both the cases, then the two things that we add should also be the same, and that will imply that minus 1 multiplied with the original vector v is nothing but the additive inverse of the vector v. Alright, so moving on to the next result. So now we prove the result that the additive inverse is unique for a given vector. So we start with the fact that the null vector is unique, and we assume another vector w to be another additive inverse. So if we add the vector with its additive inverse, it must result in a null vector, and similarly the case over here. So we are assuming that w and w and this guy are two different additive inverses, but since our null vector is unique, these two guys must be the same, which means that our w should be equal to minus v because these both are getting added to the same quantity. So that proves that w must be equal to this guy, and our assumption initially was that w is different than this guy, but it is also an additive inverse, but this proves our assumption is wrong, and therefore the additive inverse should be unique. So we have proved all the four implications of the features and properties of the vector spaces, and now we move on to an example wherein we check whether the given set is a vector space or not. So in this example we are going to consider a set of all entities of the form A, B, C, where the entries are all real numbers. It means that A, B and C should be real numbers. Okay. So once I have done this, if I want to check whether it's a vector space or not, the first thing that I need to do is I have to define how to add the two elements of the set and how do I multiply each element with a scalar, and that is what I have defined here. So addition and scalar multiplication are defined as follows. So ABC plus DEF it will be equal to a plus d, b plus e and c plus f, and alpha times abc will be equal to alpha a, alpha b and alpha c. Okay, so now the question is, does this set form a vector space? And to do this we have to verify whether this set agrees with all the properties that we have discussed so far. So first of all, a, B, C, D, E, F must belong to the real numbers, because that is only then will each of these elements will be part of this set V, where V is basically the set of all objects of the form XYZ for all XYZ belongs to real numbers. That is how we defined the initial set. Okay. So now if all the properties are satisfied, all the properties of a vector space are satisfied, then V will be a real vector space. And the reason for V being a real vector space is that if you multiply alpha, the result will be alpha A, alpha B, alpha C, and for this to be closed under scalar multiplication, alpha must also be real. And this implies that since alpha is real, any scalar that has to be multiplied with this vector must also be real. It means that this vector space is defined over a real field, and therefore this is a real vector space. Okay. Okay, so let us verify these properties. That is, first of all we have to verify that they are closed under vector addition and scalar multiplication. So under vector addition, we see that ABC plus DEF will give A plus D, B plus E, C plus F, and since all of these are real numbers, these guys will also be real, and therefore this entire thing will be an element of the initial set V, and therefore it is closed under addition. And similarly, if alpha is real, then alpha A, alpha B, alpha C are also going to be real, and therefore they will also belong to the vector space, to the set V. We haven't yet verified all the properties, so we cannot say that it's a vector space still. So, and this will be true only if alpha belongs to the set of real numbers, and therefore this is defined in a real field. All right. So moving further, so alpha times one element plus the other element, so this is the distributive property, is going to be equal to alpha times ABC plus alpha times DEF, and you can actually check this very easily. And this in turn is going to be alpha A, alpha B, alpha C, alpha D, alpha E, alpha F. All of them are going to belong to the set V, and therefore this property is also satisfied. And then this is distributive property with respect to the scalars. Alpha plus beta times ABC is equal to alpha times ABC plus beta times ABC, which is also satisfied. So all these properties you can easily verify this. Alpha times beta plus alpha times beta ABC is equal to alpha beta times ABC. This is the associative property, and if you add, the order of addition also is not going to matter, which is the commutative property. And so this is the associative property with respect to addition, and what it means is that if you add these two first and then add it to this guy, it is same as adding these two first and then adding it to this guy. So all of these properties are satisfied. Also, we can define a null vector as 0, 0, 0, because any vector added to this guy is going to result in the same vector. So this is the null vector, and you can also check that it is going to be unique by the same reasoning in which we proved it. Also, we have the inverse vector under addition, which is nothing but minus a minus b minus c. If I add them, it will result in a null vector. So this is showing that all the properties are satisfied, and therefore we can say that V forms a linear vector space indeed. Now, if the rules of addition had changed, or if I had defined the elements in a different way, then one or more of these properties would be violated, and then we would not have become a linear vector space. So one such example over here is that if you consider another set V dash whose elements are of the form A, B, and the third element is always 1, then and with the same rules for addition and scalar multiplication. So I am not changing the rules of addition and scalar multiplication here. So that means that AB1 plus DEF, so AB1 plus DEF will be equal to A plus D, B plus E, 1 plus 1. But since this is 1 plus 1, this is going to be equal to 2, and which means that the third element is no longer equal to 1, which means this guy is not going to belong to the set V dash, which means that this is not closed under addition, and therefore the first property itself is being violated, and therefore this is not a linear vector space. Okay, so in a similar manner, if I had defined the rule for adding this in a different way, then depending on that rule, whether it will satisfy the properties or not, that condition is also going to be different, and therefore you have to be careful and check all of these properties with respect to the rules that are defined for adding the two elements and multiplying it with a scalar. So in the upcoming videos, we are going to discuss some more examples in detail so that this concept becomes clear. And in next couple of videos, we are going to discuss the concept of linear independence and how to find the dimension of a vector space. So thank you for watching. I will see you on day 3. Take care.